Hello students, welcome back to Algebra 2. Today we're going to be talking about trigonometric functions at any angle. Now, before we get into this, we're going to be relying heavily on an idea from geometry that I just wanted to review. So, we have two special right triangles. The first one is a 30, 60, 90 triangle, where we have the angles 30, 60, and 90. Now, in geometry, we learn that the ratio of the short side to the long side to the hypotenuse is if the short side is n, the hypotenuse is twice as big, and the longer side is the short side times the square root of 3. The other special right triangle that we have is a 45, 45, 90 triangle. Now in a 45, 45, 90 triangle, if one of the legs is n, the other leg has to be n because it's an isosceles triangle, and then the hypotenuse is n times the square root of 2. Now, not to give anything away, but we are going to be dealing with a situation where the hypotenuse is always 1. So that means that if I have a 30, 60, 90 triangle and the hypotenuse is 1, that means that the shorter side has to be a half and the longer side has to be the square root of 3 over 2. 1/2 times the square root of 3. If I have this 45, 45, 90 triangle and the hypotenuse is 1, then I would divide by the square root of 2, so this would be 1 over square root of 2, but I'm not allowed to have a radical in the denominator, so I'm going to multiply by the square root of 2 over the square root of 2 to rationalize it, so I get the square root of 2 over 2 is how big this side is, and then of course the other side is going to match it. So those two triangles in red are worth memorizing because they're going to come up a lot in the upcoming chapters. Now, let's get into trigonometric functions at any angle. So let -4, 3 be a point on the terminal side of an angle theta in standard position. Evaluate the 6 trigonometric functions of theta. So, first thing we should do is go ahead and draw our angle in standard position. So, of course, vertex is at the origin. Initial side is pointing towards 0 degrees, 90, 180, 270. Now, -4, 3 would be -1, 2, 3, 4, 1, 2, 3. Right there. And so what we're going to do is draw the terminal side like that. And then our angle is right here, theta. Now, this is something that we're not used to doing because anytime we do trigonometry, it's always done with a right angle. And as you can see here, there is no right angle, except yes, there is. What we're going to do here is we're going to find the reference angle. And in order to find the reference angle, what I'm going to do is take the terminal side and I'm just going to drop a line straight down to the x-axis. And I'm going to use this right triangle right here in order to do my trigonometry. So if I have this right angle here, I know that if this point is -4, 3, this horizontal side of the triangle has to be -4, and the vertical side has to be +3. I'm going to take this out of the picture just so I can make it bigger. -4, 3. So we can just go ahead and use the Pythagorean Theorem here. A squared plus b squared is equal to c squared to get 3 squared plus -4 squared equals c squared. And that'll be 9 plus 16 equals c squared, 25 equals c squared. So therefore, c is equal to 5. So now I'm going to use this angle right here as theta. This is the central angle. And I will just say from theta, going straight across, there's the opposite, there's the adjacent, and there's the hypotenuse. Which means sine of theta is opposite over hypotenuse, so that would be 3 over 5. Cosine of theta would be adjacent over hypotenuse, so that would be negative 4 over 5. Tangent of theta would be the opposite over adjacent, so that would be negative 3/4. And then to get the other 3, I just flip them over. So the cosecant of theta is 5/3. The secant of theta is negative 5/4. And the cotangent of theta is negative 4/3. Now, we get into an interesting situation here that we can use to our advantage. I just want to point out what would happen if the hypotenuse was 1. So let's go ahead and draw a triangle, and let's make the hypotenuse 1. Now, along the horizontal axis, let's just put in a variable there. X is normally horizontal and y is normally vertical. So if the hypotenuse is 1, watch what happens. The sine of theta is equal to the opposite over the hypotenuse, which would be y over 1. The cosine of theta is equal to the adjacent over the hypotenuse, which would be x over 1. And then the tangent of theta would equal opposite over adjacent, so that would be y over x. Now, since the hypotenuse is 1, we could say that the sine is just y, the cosine is just x, and then tangent is still y divided by x. Now, this particular fact right here leads us to develop something called the unit circle. The unit circle is a circle with the origin, with the center at the origin, with a radius of 1. So let's draw a picture of that. Here's the center at 0, 0, and then I'm going to have here's 1, here's 1, here's 1, and here's 1. And I'm just going to have a circle that connects all of those 1s. We'll just make it a little thicker right there. So the nice thing there is that if this unit circle has a radius of 1, then any point that I pick on here, I'm going to go ahead and make my initial side here in pink, and then I'm going to make my terminal side right here in red. This is going to be some point x, y. So for that theta, if I can figure out what point this lands on, I can just simply say that sine of theta is y, cosine of theta is x, and then tangent of theta is y divided by x. Or if we want to push it a little further, we could say tangent of theta is y over x, but we know y is the same thing as sine, so I could say tangent is sine divided by cosine. And of course, to figure out the other 3, I could just flip those over. So cosecant would be 1 over y, secant would be 1 over x, and cotangent would be x over y, or cosine over sine. Now, one of the things that we can do with this is we can use the unit circle to find trigonometric values of quadrantal angles. Now, quadrantal angles are simply the ones that define the quadrant. So that would be 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then 360 degrees, which is of course coterminal with 0. So let's say let's start with 0. What are the trigonometric values of 0? Now this is weird because if I draw the angle 0, it would be right here. And this is very difficult to do in our traditional sense because at 0, we would try to do the opposite, but going across to the opposite, there's no angle there. It's not actually a triangle. But we can say that this point right here is the point 1, 0, where 1 is the x and 0 is the y. So, therefore, I can say sine of 0 is the y value, which would be 0. Cosine of 0 would be the x value, which would be 1. And then the tangent of 0 would be y divided by x, which would be 0 divided by 1, which is 0. We can take this further and say that the cosecant of 0 would be, now this would be 0 over 1, so that would be 1 over 0, and hopefully you remember this is undefined. Can't divide by 0. The cosine would be, this is 1 over 1, so if we flip it over, the secant would also be 1 over 1, so the secant of 0 is still 1. And then the cotangent of 0 would be 1 over 0, which again is undefined. Now, we could do that again. Let's try 270. So 270 degrees is going to go right here, giving us this point 0, -1. So sine of 270 is going to be equal to the y value, which is -1. Cosine of 270 will be the x value, which is 0. And then tangent of 270 is the sine over the cosine, the y over the x, so -1 over 0, undefined. Flipping these over to get the cosecant of 270 would be, this is -1 over 1, so if I flip it, it would be 1 over -1, which is still -1. The secant of 270 would be, this is 0 over 1, so if I flip it over, I'd get 1 over 0. That's undefined. And then the cotangent of 270 would be 0 over -1, and again, that's, nope, that's not undefined. I'm sorry, that's 0. Okay, now let's put it all together. We're going to use reference angles to evaluate functions. So again, I want to remind you that our two special right triangles are the 30, 60, 90 triangle, and if the hypotenuse is 1, that means that the shorter side is a half and the longer side is square root of 3 over 2. The other one is the 45, 45, 90 triangle, and if the hypotenuse is 1, then both of the sides are square root of 2 over 2. So, question A is asking us to evaluate tangent of -240 degrees. Now, quick note, when you do your homework, it's going to say, evaluate the following without using a calculator, and really what they mean is evaluate by using reference angles. So we want you to draw this out and do the calculations on your own. Could you just type in tangent -240 into a calculator? Yes, but the point of this is to practice doing it with reference angles. So I'm going to go ahead and draw the tangent of -240. Let's draw 240 in standard position. So here's 0. And then I would go 90, 180, and then after 180, I would go up 60 more degrees to get to 240. Okay, so that would be 240 degrees. Now, using the reference angle, I'm going to just drop this down right here. If this right here is 180, that means that this piece right here has to be 60. So that means I've got a 30, 60, 90 triangle right here. We're going to assume we're using the unit circle, so that means that the hypotenuse is 1. So this means this is 1/2, and this is square root of 3 over 2. Which means this point right here, we did go to the left, so that would be -1/2, and then the square root of 3 over 2. So tangent of -240 would be the y divided by the x, so that would be the square root of 3 over 2 divided by -1/2. And then I can use my fraction knowledge to say, well, that's the same thing as -3 over 2 divided by -1/2, which is the same thing as square root of 3 over 2 times -2 over 1. And then I can just cancel these out, and then multiplying, I get negative square root of 3. And that's the answer. Let's do the other one. Okay. Cosecant of 17 pi over 6. Cosecant of 17 pi over 6. Now, before I move any further, the radians in this can be a little bit intimidating, so I just want to think about this for a moment, and I'm just going to write out what I'm thinking. Pi radians is 180 degrees. So therefore, pi over 6 radians is 180 divided by 6 degrees. So that would be 30 degrees. So 17 pi over 6 would be 30 degrees times 17. And no judgment if you don't know your 17s. 510 degrees. Okay, so now just to put that into a smaller form, 510 minus 360 is 150 degrees. That's a little bit easier to manage than 17 pi over 6. So let's go ahead and draw that. Here's 0, 0, and then here's my initial side. And then I'm going to go all the way around once, that's my 360, and then I'm going to go another 150 degrees, which would be, oops, let's do that a little bit better, right there. Now, if we did 150 degrees, that means this line right here is 180, and we stopped a little bit short of it, which means that the reference angle right here would have to be 30 degrees, which means I've got another 30, 60, 90 triangle. So again, if this is 1, the shorter side would be 1/2, and the longer side would be square root of 3 over 2. So that means that this point right here, the x value is negative square root of 3 over 2. And the y value is positive 1/2. So we're asking for cosecant. I'm going to start off with sine because that's the inverse of it. Sine of 17 pi over 6 is equal to just the y value, so that would be 1/2. So in order to find the cosecant of 17 pi over 6, I would merely flip that over. The answer would be 2.